This video is a review of some of the math that you need for solving nuclear reaction kinetics problems. This is question number 16 from the course packet. If 15 grams, and I forgot to say this, of a radioactive isotope decays for 10 years and 14.2 grams remain, calculate the rate constant, the half-life, and how much remains after 50 years. So the most important thing here is to do everything with first-order kinetics. So we're going to start with the integrated rate law form for first-order kinetics. All nuclear reactions are going to obey this rate law. All right, and so to find the rate constant, we're going to plug in the values we're given. Now, the 15 grams is the amount we originally had, so that's going to be our A naught. We have a time of 10 years, and we have 14 grams remaining after that time. So that's our A value. So we're going to plug in ln 14.2 equals negative of the rate constant times the time plus ln of the original amount. Now, because the units always cancel out with natural logs, it doesn't matter that these are grams instead of molar as we were using in solution chemistry, because again the units cancel out. So, so we're going to move the ln 15 over to the other side. And whenever you feel like it, you can convert these into numerical values with your calculator. I'm going to do it at the end. Divide both sides by negative 10 years. So K now is going to be 14.2 natural log minus 15 natural log divided by negative 10, and that's going to give us 0.00548. Units here, notice unitless in the numerator, years in the denominator. Move that to the top, that becomes inverse years. All right, on to part B. So for the half-life, we're going to use the equation that we used in class for this. The half-life, which has this goofy T1 half symbol, the half-life is going to be 0.693 over K. So 0.693 divided by our K value, and that's going to give us 126. Notice that years, inverse years is in the denominator. When it comes to the numerator, that becomes years. So that's our T1 half. It makes sense that our half-life would be in years. Now, for the final part of the question, we're asked how much remains after 50 years. So 50 is going to become our new A. So we're going to start over ln of A equals negative kt plus ln A naught. And we want to know how much, so ln of A is our unknown. We know K now. This time we're plugging in for 50 years. And again, our original amount was 15 grams. Notice that years and inverse years cancel each other out. So that gives us a value of 2.434. Now, remember from algebra, when you're solving for the argument of a logarithm, you raise it to the power of the base, which for natural logs the base is this cool number e. It's the natural log base. So that gives us that A is going to be equal to this number raised e to the x. That's just the inverse of the natural log on most calculators. That's going to give us 11.4, and the units there is grams. Notice that this is less than we started with, which is what we expect. It's also less than what we had after 10 years back in Part A. So this is a pretty reasonable answer. Again, this is a walkthrough of a problem to give you an example of the math necessary for kinetics of nuclear reactions.